Okay, so today we will discuss uniform continuity and absolute continuity. Okay, so let's see the first uniform. We have already seen the continuity definition. If we let A, which is a subset of R, and let F a mapping from A to R, set of all real numbers A to R, then the following two conditions, then following following statements are equivalent. That is, the first statement is that f is continuous, f is continuous at every point u belongs to A, and second is given epsilon r greater than 0 and u which is an element of A, there is a delta which depends on epsilon r as well as the point u and greater than 0, such that for all x belonging to A, for all x such that x belongs to A and satisfy the condition mod x minus u is less than delta which depends on epsilon u, then the mod of f x minus f u is less than epsilon. So, this we have discussed already. A function is continuous at a point u if for a given epsilon there exists a delta such that mod of f x minus f u less than epsilon whenever mod of x minus u less than delta. And here we have seen that this delta depends on the point. If I change the point, the correspondingly delta will change. Okay. So, what this shows? This shows the function f changes its behavior when the point changes. Maybe the behavior, suppose for some point the function is very slowly changing the their values, and for some near to some point it changes very rapidly. For example, if we take the sin 1 by x when x is not equal to 0, if we look this function, then this function is changing very rapidly when the point is very close to 0. It goes very up and down from plus 1 minus 1 to plus 1 and very rapidly it goes. So, we are interested in such type of functions where the change is smooth, say, okay. Or we can say that we are interested the delta which is independent of u, and that leads the concept of uniform continuity. Okay. So, the function we say it is continuous pointwise here, but pointwise means delta will depend on the u. So, we wanted a definition in which the delta is independent of u, and that leads to the definition or concept of uniform continuity. So, let us see the definition of uniform continuous function. Continuous function. Let A be a non-empty subset of R, and let F is a mapping from A to R. We say F is uniformly continuous. F is said to be uniformly continuous on the set A, if for each epsilon, greater than 0, there is a delta which depends only on epsilon, a positive delta which depends only on epsilon and independent of the point u of A, such that if x and u are any two arbitrary point of A or any number satisfying the condition mod of x minus u is less than delta, depends on epsilon only, then mod of f x minus f u is less than epsilon. So, what this shows is that a function is said to be uniformly continuous over the set A. Remember, when we say the function is continuous, then we can say function is continuous at a point. So, at a point we can identify a delta which depends on, but when we say the function is uniformly continuous, then saying uniform continuous at a point is meaningless. It will be continuous over a set. So, a function is said to be uniform continuous over the set A. We mean that if for any epsilon greater than 0, if we are able to get a delta which is independent of the points of the set A, such that if whenever we pick up any two arbitrary point set in the delta neighborhood of this, then corresponding fluctuation f x minus f u will remain less than epsilon, the value of this. For example, if we take the function f x equal to say 2x, okay, and this f x equal to 2x for all x belongs to say real number r. Okay. Now, if I consider mod f x minus f u, where the u and b are the point, let x and u, these are the points in R, okay, and satisfy that condition. So, consider this is equal to 2 x minus 2 u, which is equal to 2 times x minus u. So, if we choose delta which depends on say epsilon u as epsilon by 2. So, obviously, this delta is independent of u, because this is basically we are taking delta to be epsilon by 2, whatever the u may be. So, it is independent of this. So, if I take delta this, then obviously, this part for all epsilon greater than 0, then this condition holds less than epsilon for all x and u belongs to R, such that mod of this x minus u less than delta. Is it okay? And this is independent of delta is independent of the u and positive quantity. So, this function will be considered f x equal to 2a, we can say it is uniformly continuous over the entire real line, Okay. However, there are the functions which are only continuous, but not uniformly. For example, if we take the function, so f x equal to 2x is uniformly continuous over any set A which is subset of R, over any subset of R, okay, or in entirely. Now, take a function g x, say 1 by x, for x belonging to the set A, which is the set of those points of real number such that x is positive. Okay. Now, we claim that this function g is continuous, but not uniformly over A, not uniformly, continuous at each point of A, but not uniformly. Let us see how. Let us consider Gx minus Ga, Gu. Gx minus Gu, this is equal to what? 1 by x minus 1 by u, which is the same as u minus x over ux. Okay. Now, if u belongs to this, if u belongs to A, suppose, okay, u belongs to A is given, there we wanted to test the continuity is given. So, if we take delta which depends on u as the infimum of u by 2 and u square epsilon by 2. So, let epsilon greater than 0 be given. Here we let us write, let epsilon greater than 0 be given, and let us pick up the point u at which the continuity is tested. So, now choose the delta is this. So, when you take this delta, then if mod of x minus u less than delta, okay, and delta which is depending on epsilon u, then I can choose. So, suppose first it is less than u by 2, then so picked up take delta as u by 2. So, what happen is this shows that x minus u is less than u by 2, or this implies that x lies between 3 by 2 u and half u, because x minus u is less than u by 2. So, it becomes less than 3 by 2, and then u minus x is that is x minus u is u minus u by 2, x greater than this. So, this is greater than. So, it lies bound with this. Therefore, the bound for this, therefore, 1 by x can be x is greater than u by 2. So, 1 by x will be greater than x is less than. So, 1 by x. So, 1 by x is less than, because it will be x is greater than this. So, 1 by x will remain less than 2 by u. From here, once it is 2 by u, then the condition, in the condition which we have taken as Gx minus Gu, in this case what we get mod of this, this is less than equal to u minus x mod over ux. So, u into x, x means 1 by x. So, it is 2 into y. So, it becomes the 2 by u square into u minus x. Now, further choose delta to be this thing u square epsilon by 2. Okay. So, once I am taking delta to be this, another one I am taking this. So, what we get is from here, this shows that this part mod of Gx minus Gu is less than equal to delta, means mod of u minus x is less than delta. So, this is less than 2 by u square into u square by 2 epsilon, that is epsilon. Okay. So, this holds that if x minus u is less than delta for all such x, then Gu x minus Gu will be less than epsilon, and this is true. So, this shows that G is continuous at u belongs to A. Clear? But here the delta which you are choosing is coming which depends on u, which depends on u, is positive quantity. Okay. But what happens to this? Sorry, this is not, this is each individual delta is positive when u is taken to be there. But when you take the infimum value of this, when you take the delta as the infimum of all such, then what happens to that? Infimum of delta, here delta depends on epsilon u, So, G is pointwise continuous. Pointwise continuous, but what is the infimum of all such deltas? Delta, infimum of all such delta which depend on epsilon u and u is greater than 0. The infimum value of this is coming to be 0. Why? Because each delta here is nothing but either u by 2 or u square by 2. So, u is greater than 0. So, each delta is greater than 0, but when you take the infimum value of this delta over u, then this infimum will come out to be 0. So, we are not getting a delta which is greater than 0. So, for a given epsilon r greater than 0, we cannot get delta which depends only on epsilon r, and greater than 0, such that condition mod of g x minus g u is less than epsilon r, provided mod of x minus u less than delta hold. This we cannot get. Therefore, G is not uniformly continuous. Okay. So, we have seen the example where the function is continuous pointwise and the function is uniformly continuous. Now, to show the uniform continuity, we require the delta where independent of the point over the entire set. So, that is not that easy. So, what we can develop the test which will give the at least sufficient criteria when the function is not uniformly continuous. So, we will just state those results without proof, the criteria for the non-uniform continuity. So, and the non-uniform continuity criteria. This will be needed. So, proof we are just dropping, but it is can be easily done with the help previous knowledge. So, let A be a non-empty subset of R and let F is a mapping from A to R. Then the following statements are equivalent. The first statement says F is not uniformly continuous. Uniformly continuous on A. Second statement says that there exists an epsilon naught greater than 0 such that for every delta greater than 0 there are points say x depends on u, x depends on say delta, not x depend on delta, and then u depend on delta in A such that the mod of x delta minus u delta less than delta and mod of f x delta minus f u delta is greater than or equal to epsilon naught. And third statement says there exists an epsilon naught greater than 0 such that, and the two sequences, and two sequences, say xn and un in A such that limit of xn minus un over n is 0 and mod of f of xn minus f of un is greater than equal to epsilon naught for all n belongs to capital N. Let us see this what is. So, uniform continuity criteria says if suppose function is not uniform, then by the definition of not uniform means a function is said to be uniform continuous if at over the set A, if for each epsilon there exists a delta which depends only on epsilon not on the delta, such that the difference of f x minus f u can be made less than epsilon provided the point are in the delta neighborhood. So, if the function is not uniformly continuous, it means this condition will be violated. If we choose the point in the neighborhood of delta, the images of this, the fluctuation may not be less than epsilon, it can exceed to any number, arbitrary number epsilon naught. So, that is why what he says is that if f is not uniformly continuous, then there exists an epsilon naught such that whenever the point x and u are in the delta neighborhood, the corresponding images exceed that bond epsilon naught greater than. Similarly, this is in a Cauchy definition, this is Haney's definition. Instead of choosing the two arbitrary point, if we picked up the two sequence x n by n which are tending to 0, the limiting both are difference of this is tending to 0, means x n and u n are very close to each other as n is sufficiently large, then but the corresponding images is not close, it greater than equal to some positive number epsilon naught, then we say the function f is not uniformly continuous. Okay? We got this. Now, this criteria can be applied very directly. Suppose I applied this function to show g x which is 1 by x is not uniformly continuous, on the set A where x is greater than 0, set of all real number n. So, what we do is we have to pick up the two arbitrary sequence. So, let x n I choose the 1 by n and u n I take to be 1 over n plus 1, both are in A, and the difference of these two sequences obviously x n minus u n, this goes to 0 as n tends to infinity, but what is our g of x n minus g of u n? This mod is nothing but what? G of x n is nothing but n plus 1 minus n, that is 1, which does not go to 0. In fact, it is greater than equal to any number epsilon naught. Therefore, G is not uniformly continuous. So, G is not uniformly continuous. That is what. Now, uniform continuity when it is function is defined over a closed interval and if function is continuous, then it will be uniform continuity. So, this result is known as the uniform continuity theorem. The theorem says let I be a closed bounded interval and let f which is a mapping from I to R be continuous on I, then f is uniformly continuous. Uniformly continuous on I. So, what he said, if the function f which is continuous over a closed interval, closed and bounded interval, then function must be uniformly continuous. So, suppose f is not uniformly continuous. On I. So, I can use one of the criteria which I listed earlier. I will take the in the form of the sequence, okay, by now. So, what we did? So, by the previous result or previous theorems, where the criteria are there, we can choose. Then there exists a epsilon naught greater than 0 and two sequences xn and uns in I, such that the difference between these two, that is limit of this is going to 0, means difference is very very small, say 1 by n, and but the mode of f x n minus f u n, this difference exceed by this epsilon naught for all n. So, this is by the criteria when non-uniformly continuous criteria. From here we are getting this part. Okay. Now, since I is bounded and the sequence xn and uns both are the sequences belong to I. So, by Bolzano-Weierstrass theorem, every bounded sequence has a convergent subsequence. So, there is convergent subsequences. There is convergent subsequences, say x n k, and there is convergent subsequence. Let us take first this part, then we can take belongs to this. So, there is a convergent subsequence x n of x n that converges to an element z, to an element say z belongs to I, z that converges to z. Now, we wanted to show z is a point in I, which follows because I is closed. Since I is closed, so all the limit point of a sequence in I must be point in there. So, this and also all the sequence x n k lies between the lower and the upper bound of this interval. So, by the Sandwich theorem, the limit of this sequence x n k must be the point in I. So, this implies if since I is closed, the limit point z belongs to I. Okay. Similarly, we can say we can also show we also claim that the sequence u n will have a subsequence u n k in I whose limit point belongs to I. Limit point belongs to I, but the limit point of u n k and x n k will be the same, but limit point of u n k and the limit point of z x n k will be the same. The reason is because if I consider the u n k minus z, then this can be written as the u n k minus x n k plus x n k minus z. Now, this term is less than equal to k by condition which we are choosing, because both are in A and we are choosing the interval neighborhood in such a way so that this is less than equal to k, and this converges to z. This is the limit point of this, so it goes to 0. So S tends to total tends to 0. Therefore, both will have the same limit point. Once they are having the same limit point, therefore f so f is so z belongs, so f is continuous. Now further, since f is continuous at z, then both the sequences, then f of x n k and f of u n k must converge to f z, because x n k goes to z. So, f of x n k will go to f of z, u n k goes to z. So, f of u n k will also go to a, because f is continuous. So, once they are continuous, but the given condition is, given hypothesis is that mod of f x n minus f of u n is greater than equal to f sin naught. This is given. So, the contradiction, and contradiction is our, because our wrong assumption that function is not uniformly continuous. So, therefore, f is uniformly continuous over a. That shows the result. Okay. So, this proves that uniform continuity. Now, this is one more results which we say, then we come to the if theorem is, if f is a mapping from A to R is uniformly continuous, on a subset A of R, and if x n is a Cauchy sequence, in A, then f of x n, this sequence is a Cauchy sequence in R. It means, if f is a uniformly continuous function, then it will transfer the Cauchy sequence to the Cauchy sequence. The proof is, let x n be a Cauchy sequence. In A. Okay. We wanted to, and f is given to be, and f is given to be uniform continuous over A. So, by definition of the continuity, let for a given f final greater than 0, we can identify a delta. There exists a delta which depends only on f final greater than 0, such that the mod x minus u is less than delta, such that for if x comma y, x comma u belongs to A, satisfy this condition, then f of x minus f of u, this is less than f sin. Okay. So, let it be 1. Now, it is given the sequence x n is a Cauchy sequence. So, since x n is a Cauchy sequence, so by definition of Cauchy, so for a given f sin greater than 0, for given delta, we can say there exist for given delta greater than 0, there exists an h which depends on delta, such that the difference between any two arbitrary term of the sequence after a certain stage can be made less than delta for all m n which are greater than equal to h. This is 2. Okay. Now, by this same delta, if by the same choice of delta, since xn is less than this, so if you take x equal to xn, u equal to xn, so from 1 it follows that f of xn minus f of xm, x of xn minus f of xn, mod of this will be less than epsilon for all nm greater than equal to h. This shows the sequence fxn is a Cauchy sequence in R. So, that is proved the result for. Okay. Now, we come to the thing which is say our absolute continuity. That is a new absolute continuity. Absolute continuity means a function f x is said to be absolutely continuous in the interval say a b if corresponding to an arbitrarily chosen positive number epsilon, another positive number delta can be determined such that for a sequence of non-overlapping interval, non-overlapping intervals h r k r, open interval h r k r, defined in a b, the sigma of mod f of h r minus f of k r is less than epsilon provided sigma of k r minus h r this length is less than delta. So, what is here? It means that is we can say, so we say the effect that is f x is absolutely continuous function. The meaning of this is absolute continuous over the interval a b, if corresponding to a given epsilon, a number delta exists, such that in a countable set of non-overlapping intervals, of total length, I am not using the measure, of total length less than delta, the sum of the fluctuations of the function is less than epsilon, So, let us see what is the meaning of this is. Suppose we have a interval a b and a function f is given. We say this function is absolutely continuous in the interval a b if b for a given epsilon greater than 0. If we have a non-overlapping intervals, means divide this one, say in this non-overlapping, say here this is like this. If I take this non-overlapping intervals and so on like this. So, if we take a countable number of non-overlapping interval of this whose length is less than delta. So, we have to take a small portion. Suppose I take this small portion, this. Now, this small portion is total length is delta, total length of this is delta. So, this small length we can over this small interval we can find a non-overlapping intervals such that sigma of this length kr minus hr, this length is less than delta. These are countable 1 to infinity, r is 1 to infinity. Total length is less than delta. So, for a given epsilon, say this epsilon is there. For this given epsilon, we can find a delta such that whenever we have a non-overlapping intervals, countable number of non-overlapping intervals whose length is less than delta, then corresponding fluctuation over these sub-intervals, the total sum of this corresponding this fluctuation should not exceed by epsilon. If so, then we say that is sigma of mod f of hr minus f of kr, this should be less than epsilon 1 to infinity. So, if the total fluctuation of the function over this sub intervals is less than epsilon whenever the points are in this intervals in countable number of intervals whose length total sum is less than delta, then function is said to be an absolutely continuous function. So, obviously, every absolutely continuous function is continuous. As a note, we can say function which is absolutely continuous in the interval a b is also continuous in accordance with Cauchy definition. Because what we do, we replace it, the total set kr we consider of single interval. We can the sum of these we can replace by a small interval, total sum is less than delta, and then correspondingly here we get the total fluctuation is less than epsilon. So, this will be obviously true, consist of this, okay, less than then the condition of uniform continuity. Similarly, we can also say that we may take the same interval, single interval length delta, and definition of uniform continuity is also satisfied over this. Uniform continuity is also satisfied. So, function which is absolutely continuous is a continuous ever, and for B also we say it is uniformly continuous. And uniform continuity condition is also satisfied if we choose the kr to consist of single interval of length delta. Okay. Converse is not true. That is, A function which is continuous may not be absolutely continuous in that interval. That is, a function which is continuous in the interval a b may not be absolutely okay, absolute TLY absolutely continuous in that interval. Okay. A function which is continuous may not be absolutely continuous. For example, if we take the function f x, which is defined as x sin 1 by x when x is different from 0 and 0 when x is 0. We know this function is a continuous function. This is a continuous. This we have seen, this function f x is continuous. This we have already seen. So, nothing, because the limit of this f x, because the limit of f x continuous at 0, okay, continuous at 0, and otherwise also is continuous in the total limit as x tends to 0 is the value of this function is coming to 0, which is f 0, and for other point at x belongs to 0 1 interval. In fact, entire interval it is continuous, because at the point 0 the value is coming to be this and continuity follows. Okay. Now, it is not absolutely continuous, we claim, but this function f x is not absolutely continuous on the interval 0 1. Why? It means the condition of the absolute condition is not satisfied. That is, if we choose the infinite number or countable number of subintervals whose total length is less than delta, but the fluctuation may not be less than epsilon. So, that is what. So, suppose I divide the interval 0 1 in each of these subintervals, we get into subintervals say 1 by r pi 1 over r plus 1 pi. These subintervals where r is 1, 2, 3 and so on into subintervals, and in each intervals in the subintervals 1 upon r pi and 1 upon r plus 1 by r is 1 to 3. The fluctuation of the function, f x, which is x sin 1 by x, exceed by this number 1 by r plus 1 pi. Let us see why. Over this function, the region is over this function, this is our interval 1 by r pi, this is our interval 1 by r plus 1 pi. The function x sin 1 by x, if we look the function f x, which is x sin 1 by x, at the end point the sign of this is 0, because it is an integral multiple of pi. So, basically the function will go like this, because at this end point r pi or r plus 1 pi, this value will give the value 0. So, the fluctuation of the function, the value of this minus the value of this will be something which is greater than this number. Now, here the maximum value, suppose I take x equal to say let us choose x to be 2 over 1 by x to be 2 r plus 1 pi by 2. Okay, 2r plus 1 pi. So, x will be 1 upon this line, say here. Then what will be the sign of this value? Sin of 1 by x is 1, because odd multiple of this 1, and this value will give the f of x 2r plus 1 pi by 2. The 1 upon 2r plus 1 pi by 2. So, this will be greater than the value at this point, r plus 1. So, fluctuation will be exceed by this number, which is greater than this, okay, by this. Clear? So, we get from here is that the fluctuation is exceeding by this. Therefore, the sum of the fluctuation. So, sum of the fluctuation in the sequence of intervals, say 1 by r pi, then 1 over r plus 1 pi, this sequence of intervals corresponding to r is equal to n, n plus 1 and so on, is greater than, if I take the sum, is greater than 1 by pi, 1 over n plus 1, 1 over n plus 2 and so on. But this series is a diverging series. So, this cannot be made as small as we please, greater than. So, it is greater than by any assigned positive number a. Therefore, for the series, therefore, this large number cannot be, so it is not a. So, the function f x, which is x sin 1 by x, x is different from 0 and 0 when x 0 is not absolutely continuous, absolute continuous. Okay. So, this one. Their results are, just state the one result. The result says the sum and the product of two absolutely continuous functions are absolutely continuous, So, this proof follows on by the definition, and one can go with the proof. Thank you very much.